All right, so today we're going to look at our last section on word problems, okay, which is 12.9. We're going to do some word problems today, and then we'll look at some similar ones tomorrow. Okay, so we'll spend 2 days on these.
And tomorrow, guys, going to be basically all practice with the word problems. A lot of it's going to be you guys doing them tomorrow in class. You get 1 day of practice.
Okay, somebody remind me again, what's that formula that relates distance, speed, and time? It's D equals... Yep. I usually use D for distance, R for your speed or your rate, and T for time.
So that goes with formulas?
That goes right with the formula line, correct. And guys, we didn't put lines on there for what those things mean, what the letters mean, but we figured you guys could just kind of, we left a little bit of room underneath that line to write in. So if you want to put your arrows, you want to write it below, you want to write above, that's entirely up to you.
All right, so D equals RT. Okay, usually our distances are going to be in miles. I think even in the problem I changed, I'll come right back to that. It's miles. Okay, generally, the speeds that we measure things in are going to be miles per hour. Is miles per hour used everywhere for speed? Is this the only way to measure speed? No? Does anybody know another way they measure it?
Kilometers?
Yeah, kilometers per hour. Do you know where they do that?
Like the UK, Canada, basically anywhere where they use metric systems.
Pretty much everywhere except the U.S.
A metric system.
The U.S. is one of the few countries that does use miles per hour. But yeah, you're right. All right, so we'll use miles per hour for our speeds.
Sometimes the book might put MA/HR to abbreviate it, but usually it's MPH. But just so you put both of them on there, because sometimes the way the book writes it, maybe what we give you on a test might be two different things, but it means the same thing.
Okay, and time is usually measured in hours. Okay, so even if something took, say, 30 minutes, 30 minutes is how much of an hour? Half. So if we had a word problem that had 30 minutes, Mr. Roy and I would probably write 0.5 or 1/2 of an hour, all right, to keep everything in hours. All right, these problems are already tricky enough without trying to convert between hours and minutes and things like that. So we'll try to stick with these units. Okay, does everybody have those units? All right.
Is MI/HR just miles per hour?
Yeah, it's the same thing.
Just a different way of writing it.
Yeah.
All right, so this is going to be your template that you see this week, okay, for word problems. Column 1 is going to usually be the two things that are traveling, whether it's two people, or maybe it's two cars. We just call them car 1 and car 2, or train 1 and train 2.
Might be a train, might be a bus.
These are the two things that are going to be traveling. Distance, we're going to have a distance for each thing that's traveling, a speed for each thing that travels, and a time. Okay? Hey, any questions on that? Okay, so there's our table. And really, that's all the background we're going to give you. Okay, we're just going to jump into doing, we have 5 examples listed. If we get through all 5, great. If we only get through 3 or 4 of them, that's okay too. Whatever we don't finish, let's finish tomorrow. All right, so here's our first example, which you guys already have on your paper. Okay, let's just read through it first and see what's happening. It says a train left Pennsylvania Station traveling 35 miles an hour. 2 hours later, a high-speed train left on a parallel track, so right next to it, going faster, 55 miles an hour. So eventually, even though the high-speed train left after, what's going to happen?
They're gonna pass because the slower train is slower.
Yeah, they're going to catch up and you're going to pass each other, okay, eventually. So basically, that's the question. How many hours later will the two trains meet? Okay, that's what we have to figure out. How many hours later will the two trains meet? All right, so let's figure out what we're going to call our two things. Maybe we could call it train and high-speed train, regular train, high-speed train. Okay, so let's put that in for our labels. The regular train, and we'll call it the high-speed train. Right, and we have 6 things we have to figure out. We have a distance for each, a rate for each, and a time for each. Let's go back and read through the problem. Okay, let me make it a little smaller. Let's focus on the speeds. Okay, do I know the speed of the regular train? How fast is the regular train going?
35 miles per hour.
All right, so let's fill that in here.
Yeah, put in all the stuff you know first.
Okay, do I know the speed of the fast train?
Yes.
Yep.
55 miles an hour.
Okay, so that's 55 miles an hour. And now I know something about time. Okay, what I know about time is 2 hours later. Okay, so one of these trains left 2 hours before the other one. Let's say, do we know how long either train has traveled right now? Like one of them traveled 6 hours, one of them traveled 4 hours? Do we know that yet? No. So since I don't know how long the regular train has been traveling, what letter could I use to represent the time the regular train has been traveling?
R.
You want to use R for time?
I mean, no, T.
T, yeah. Let's call this T. Okay, the regular train has been traveling a certain amount of time, but we don't know how long. But let's look at the high-speed train. It left 2 hours later. Right? Well, if you put 2T, that would mean the high-speed train traveled twice as long as the regular train. Which train is traveling longer? The regular train or the high-speed train? Which one? The regular one, because it left first. Okay? It's been traveling 2 hours longer. So what do you think for the high-speed train?
Plus.
I like the idea of minus, because minus means shorter. It is T minus 2. Let's look at that for a second. Okay, let's say the regular train was traveling for 6 hours. And then the high-speed train caught up, and it was traveling 2 less hours, right? Because it left 2 hours later. So if the regular train was traveling 6 hours, the high-speed train would have been traveling 4 hours. Okay? Because remember, the high-speed train left 2 hours later. So it has traveled 2 hours less time. Okay? It's kind of like, let's say you and your friend both headed to Boston. Okay? You left, your friend left 2 hours after you, but caught up to you. Okay? Well, what that would mean is that if you both got there in the same amount of time, your friend must have been going faster to catch up to you because they did it in 2 less hours than you did. Because you left 2 hours before them and you both got there at the same time. Okay, so they must be going faster. All right, and now the distance. Okay, let's think of it as a picture. Okay, let's look at this: the start. Okay, and this is where the two trains finally catch up to each other. Okay, so we have train 1, and then 2 hours later we have the high-speed train. Eventually, they're going to catch up to each other. When they catch up, how does the distance that the slow train and the distance that the high-speed train went compare? Right at the point when they catch up to each other. if you compare the distances, anybody see what a connection there? They'd be the same, right? Once those two trains catch up to each other, if you measure the distance from each train back to where they started, the distances would be the same, because it's where the two trains finally caught up to each other, and they're at the same point, so they must have each now traveled the same distance. Okay. Any questions on that?
Liz, what would be the answer then?
So we don't know how far they traveled, but we know they traveled the same distance, so let's call them both D. Okay, any questions on that? It's kind of like if you both start from Monty Tech and you drive to, say, exit 33 on Route 2, okay, and you got a head start. Eventually, though, even though if you got a head start, if you both meet up at exit 33, you've both traveled the same distance. You went from Monty Tech to exit 33, your friend went from Monty Tech to exit 33. You both met at that spot, so you traveled the same time, same distance. Okay. Your friend must have been going faster, though, to catch up to you, because you had a head start. All right, so that's the tricky part, okay, filling in our table. All right, now that we have our table, I want to go back and use this equation on each row. Distance equals rate times time. Okay, so let's start with our regular train. Okay. Gabe, what's the distance that the regular train traveled in our table?
35.
That's the rate of our regular train. Which column represents distance? The first, second, or third? First. So what's the distance of the regular train in our table? D. Okay. Regular train distance, we represented it as D. Distance equals rate times time. Okay, Alexis, what's the rate of our regular train? 35. And distance equals rate times the time. Justin, what's the time of our regular train? T. Okay, that's, I could put that in equation, I'll just rewrite it. That's equation 1. Okay, equation 2, we're going to do the same thing, but use the distance, the rate, and the time from the second row. Okay, Ben, what's my distance for the high-speed train? D. How about Alexis, what's my speed for the fast train? 55. And how about Alex, what's my time for the high-speed train?
T-2.
It's T-2. And what symbols do you think I need to use when I plug that in? Yep.
Parentheses.
Yes, we're going to use parentheses. Because we're going to have a distributive property. And that's equation 2. So D equals 55 times T-2. Right, now we did one of these in the warm-up. Both of these things are equal to D. So what does that mean I can do? Cal? Remember that from the warm-up? These are both equal to D. Yeah, we can plug in for D. What can we plug in for D right here? Perfect. 35T. Okay, so you take 35T, plug it in for D. All right. And now let's see what we got. 35T equals 55 times T-2. All right, next step, what am I going to do with that 55 on the outside? Caitlin? Yeah, we're going to distribute it. So we get 55t. And does anybody know what 55 times negative 2 is? Good, negative 110. Okay, next I've got the things without t on the right. I'm going to put all the numbers that have t's on the left. So Ariana, how would I move 55t to the other side? Good. I'm going to subtract from both sides.
Equals negative 20.
Yep, if you're not sure, you could just use your calculator, but that is correct. 35 minus 55 is negative 20. T equals negative 110. And what's my last step to finally find the time?
Divide negative 20 on the side.
Yep, divide both sides by negative 20. On the right side, what's a negative divided by a negative? That's gone, positive. And let's just use our calculator. 110 divided by 20. 5.5. Okay, that's our time. So now let's go back up and see what the question was asking. Okay, we have a time of 5.5 hours. And it says, in how many hours after the slow train starts will the trains meet? So, how many hours after the slow train starts will the two trains meet? What did we say? 5.5 hours. Yes. Now, what if I said this? What if I said, how many hours after the high-speed train starts will they meet? So if you were riding on the high-speed train, how long before you catch up to the slow train? Yeah?
7.5 hours? Because you add 2. Or no, you subtract.
You subtract 2.
Subtract 2. So that would be.
So how long, if you were riding on the high-speed train, how long before you catch up to the slow train? 3.5. Okay? Any question on that? All right, so if you were riding on the slow train, it's going to take you 5.5 hours. If you're riding on the fast train, it would take you 3.5 hours to catch up. All right, so those are the kind of questions as we go through. I'm going to ask you those things just to kind of get you thinking about kind of all the details of a distance problem. Okay? But that's exactly how it would be set up on the test. Equation 1, equation 2, and then your answer. Okay? Kind of like the last test. All right, example 2, a little bit different. Two automobiles are 276 miles apart, and they're starting at the same time. So there's no head start here. They're each starting at the same time, and they're going to drive towards each other. Okay. We know that their speeds are different by 5 miles an hour, and we know they meet after 6 hours. So after 6 hours, the two cars finally meet each other. Okay, so you wouldn't really use the word catching up. Usually we use catching up when two things are going in the same direction. So these, it's kind of where they meet. All right, so first thing we should do is maybe pick some labels. What should I use for my two labels? It just says two automobiles.
Like a red car and a blue car?
You could use colors for cars, yeah. Car A, car B, that's fine. Car 1, car 2. Whatever seems simple. Yeah, I like the idea of like just car 1, car 2, or car A, car B. All right, and we know that their speeds are different by 5 miles an hour. Okay, so we don't know the speed of either car. Okay, so the first thing I have to do is just represent car 1's speed. Okay, what letter could we use for car 1's speed? R, sure. Now, car 2 has a speed that's 5 miles an hour different. Okay? It doesn't really matter if we say it's 5 miles faster, it's 5 miles slower. You'll see that doesn't really make a difference. Okay? So how could I represent the speed of car 2 if it's different by 5 miles an hour? Let's say car 2 is the faster car. Yeah, let's just call it R plus 5. Now, if it should have been the slower car, that doesn't really matter. If you did it a different way, you'd get the same answers. You just might have car 1 faster and car 2 slower. But it's going to come out to the same speeds. All right? And how long does it take them to meet? How many hours go by before the two cars meet each other? 6 hours, okay? And that's 6 hours for both of them, right? They each start driving, let's say they each start driving at noon. They're going to meet each other at 6 at night. Car 1 drove from noon to 6. Car 2 drove from noon to 6. It took them both 6 hours to meet each other. Okay, so the time is the same for both of them. Okay, last thing we need to figure out is the distance. Okay, any thoughts on how I can figure out the distance? Oh, let's think for a second. Are they each going to travel the same distance?
Yes.
No, because one's faster.
Yeah, one's going a little faster. So one of the people is going to drive a little farther. Okay? If they were both traveling the same speed, then they would meet exactly in the middle. But since one person's going a little faster, they're not going to meet quite in the middle. They're going to meet a little bit apart from the middle. Okay, so let's make a diagram to kind of show you. Let's call this car 1. Let's call this car 2. And let's put the middle, just kind of estimate it the best I can. It looked like it was right about there. All right, so car 2 is going to end up driving a little farther. Let's say they meet right there. Okay? And then car 1, right there. Now, the thing that we haven't used yet is what number in this problem. We've got to use it somehow. Yeah, we haven't used the 276. Okay? What is the 276? It's the distance between the cars when they start. So it's 276 miles from here to here. All right, so let's call the distance that car 1 travels D. Okay, we don't know what it is, so let's just use a letter for it. Let's call it D. Now, here's the tricky part. This part from here to here is D. Okay? Let me mark that on that line up above. Okay? From here to here, that part is D. How would you figure out this part, the rest of it? That's the tricky part. Okay, let's think of it this way. Suppose I had $276 and I spent 10. Okay, let's pretend like I spent 10 of it. How much would I have left if I had $276 and I spent 10? Michaela? If I had $276 and I spent 10, how much would I have left? $266. right? If I had $276 and I spent 10 of it, the rest is 266. Okay? That's how you can kind of think of this. Okay? We've already covered this distance. That's D. So what is left to cover here? Not all of 276, because we've already driven that part. So it would be 276 what? Minus D. Okay? If you minus D, which is basically like covering up this part, what's left from this blue line to this blue line? Well, just take away how much car 1 drove, and that's how much car 2 drove. Okay, here's you know what? Here's another way to think of it. You and your friend are 100 miles apart. You drove 40 miles to meet your friend. How much did your friend have to drive? 60. It's the distance minus how far one of you drove. That's how far the other one had to drive. Okay? If you were 50 miles apart and you met up with your friend, if you drove 10, how much did your friend drive to meet you?
Wait, so then wouldn't it be the other way around? Because
40.
if the car 2 drove farther than car 1, wouldn't it be car 1 is 276 minus D?
No, I think that should work out okay.
Okay.
I don't. Yeah, I think that's okay. That should be okay. So that's 276 minus D. Okay, so when I get confused, that's how I think of it. You know, think of I met a friend 50 miles apart. I drove 10 miles to my friend. How far did he drive to get to me? He must have drove 40. Take the distance between us, subtract what I drove, and that's what he had to drive. Okay? All right, that's the hard part. And that is tricky. Okay, so now we've got our equations. Let's set them up. Okay, and keep in mind we're going to use this equation each time. Just fill in your distance from row 1, your speed from row 1, and your time. Okay, basically, you just put an equal sign right there, and there's your equations. Right, so anyone think they can give me equation 1? Yeah?
D equals 6R.
Yeah, D equals 6R or R6. Perfect. Okay, just put an equal sign right there. Distance equals rate times time. Okay, equation 2. My distance is 276 minus D. My speed is R plus 5. And my time is 6. Okay, any questions on that?
Would you have to distribute the 6?
Yes. Yep. I
Put
wouldn't.
it like equals 6 R?
You could put equals 6R plus 30 if you distributed out the 6. I'm going to distribute out the 6 right now. Okay? And I'm going to show you what we substitute in for D. Okay? All right, so I got 276 minus D equals, you want to tell me, Logan, what you got when you distributed that out?
6R
Yeah?
plus 30.
Plus how much?
So 30.
30, good. And now look at equation 1. What letter is by itself? D. Okay. What does it say D equals? D equals what?
6R.
It says distance equals 6R. Okay, so we're going to take what distance equals, and where am I going to plug in the 6R in equation 2? For what letter? Where the D is. Right there. Okay, so plug that in. It says distance equals 6R. So fill in 6R for D in equation 2. And then from there, it should be pretty easy. We'll just finish it up with some algebra. All right, so 276 minus, okay, don't put D. Fill in what D equals, 6R. Okay. Now, if you look at that equation, what's the only letter that's left? R. Okay. So in a minute, we're going to know the speed car 1 drove at, and we're going to know the speed car 2 drove at. But keep in mind what the question is asking. The question is not asking anything about speed. It's asking something about time. Unfortunately, we couldn't find the time right away. We have to find the speed first. It's just the way our equations worked out. Okay? So now, let's solve for speed, and then we'll figure out how many hours it took. Oh no, I'm sorry. This is from the old thing. So once we find our speed, we're done. Find the rate of each. Okay, I'm sorry about that. So find rate, and then I'll just put car 1 and car 2. Okay, so we're going to know that in a second, and then we're done. Okay, how do I move this negative 6r to the other side? Yep, I add it. Okay, so how many r's on the right side? Yep, 12r plus 30. Somebody give me my second to last step. Minus, good, minus 30. Okay, 276 minus 30 gives me 246. And what's my last step to find r? By? Good. So it seems like once we get the equations set up, you guys are pretty good at solving it with the algebra. It's just tricky to get those equations. 20.5. Now, I'm going to scroll back up, and I want you to tell me what 20.5 is. It miles per hour? Yep, miles per hour. So it says R equals 20.5. What's R based on our table?
R is the
Rate of,
speed.
well, we have two cars in this
The rate of
problem.
which thing?
The rate of the first
The rate of the first
one.
car. Good. So car 1 is going 20.5 miles an hour. So let's put that right here.
The other one will be 25.5.
Yes. How do you know the other one is 25.5?
Because it's just R plus 5.
Right. Car 2 is just going 5 miles an hour faster. So it's 25.5. Okay. That was tricky. A little tricky. But still the same idea. You're always going to have one equation where I guarantee you the variable is going to be by itself in one of them. And you just plug it into the other. Okay? You're not going to have to use elimination for any problems. Okay? Okay, any questions on that? Do you want to do the current ones opposite direction? You good?
As guys, this is another type, but we're gonna get something that's it might make the object, make it go a little bit faster or slow it down a little bit. All right, you guys, this is like, once we get through tomorrow, the review, this will be it for word problems for the rest of the year obviously you're gonna see some on the final because we covered it second half of the year, but this will be it for word problems for the rest of the year. All right, so bear with us. I know believe me, guys. I know these are tricky way to put the stuff. All right, but we're gonna try to make it as easy as we can, you guys. We're gonna let you take a majority of the word problems home on Thursday night to do before the test. All right, so you don't have to worry about doing them on Friday. You're gonna get the majority of them out of the way on Thursday night for homework. We're gonna give you that part of the test to take home. All right, because we know these are tough. All right, so we got the rate of the wind is 7 miles per hour. Took a carrier pigeon 1 hour to deliver a message flying against the wind, and 0.7 hours to come back with the wind. The trip was 6 miles each way. find the rate of the pigeon in still air. So what are the two things that we're trying to find?
Two names?
No names.
We think of the two things that are given.
Yeah, what are the two things that are given?
Yeah.
Pigeons.
But what's the pigeon doing?
Flying.
Flying where?
6 miles each way.
He's going 6 miles each way, but one way, when he's going one way, what is he getting? Is he with the wind or against the wind? Against, right? So we'll just put the word against. And guys, these things, this works the same. We might give you one that deals with like current, like the current of a river, or the rate of the wind. All right, you'll see something like that. All right, so we got against and we got with, right? Now, do we know the distance? Did we mention distance at all in that problem?
Yes, it's 7. Oh, wait, no.
Yeah, 6 miles, right? So the distance is going to be 6. That's right. It's 6 going against the wind, and it's 6 going with the wind. Now, do we know the rate of the wind? But do we know how that rate is going to affect how fast the pigeon flies? Do we say, okay, if he gets this wind, he's going to go, 8, 10 miles an hour? No, we don't know that. We know rate. We know rate. We know the rate of the wind, but we don't know how the wind is going to affect how fast the pigeon goes. But we can use this rate of 7 miles an hour in our column. If it's going against the wind, what's that going to do to the rate of the pigeon itself? Not the rate of the wind. The rate of the wind is staying constant. It's 7 miles an hour. All right? But we're trying to find the rate of how fast the pigeon's flying. Not how hard the wind is blowing. But if the pigeon is flying against the wind, what's that going to do with speed? It's going to slow it down. What operation would I use to show that slowing it down? Subtraction. So against the wind, subtract. What's the rate that's slowing it down? How fast? 7 miles an hour. We're trying to find the rate of the. We know the rate of the wind. We're trying to find the rate of how fast the pigeon's flying. So R minus 7. It's slowing the pigeon down, right? So it could be against the wind. It could be going. You could be going up. But we might say the word upstream. If you're going upstream, people that canoe, anything like that, you have to paddle harder because you're going against the current. It's going to slow you down, right? How fast you can canoe. All right. Now, how about with the wind? What's that going to do?
+7.
Yeah, it's going to be +7. So same thing if we're going upstream or downstream. Upstream, you're fighting the current. All right, it's going to slow you down. Downstream, man, that's easy. You can just coast. Right? You don't have to paddle as much because the current's taking you. All right, so we got R minus. We're gonna get we're always going to give you the rate of the wind. We're always going to give you the rate of the current. So you're just going to add it or subtract it depending on which trip you're on, upstream, downstream, with the wind, against the wind. All right, now, time. How long does it take the carrier pigeon going against the wind? 1 hour, right? It took a carrier pigeon 1 hour to deliver a message flying against the wind. So I'm going to put 1 for against. Victor, how long does it take the carrier pigeon against with the wind behind him? 0. Yeah, and guys, in the book it might say 45 minutes, all right? But we don't want to have to deal with minutes, we want to give it based on hours. 45 minutes is 3/4 of an hour, right? So it's, that goes to the decimal form, it's 0.75. So 0.75. All right, now, so we're all set. Now, Mr. Hager, do we have to do anything before we go to our equations? We're good. So what's equation 1 going to be? Yeah, just take what like Mr. Hager said, equal sign here, equal sign here. 6 equals r minus 7 times 1. Mr. Hager wants me to put parentheses around this. Put the 1 here. All
In
right.
this case, we're just distributing a 1, so
Yeah.
it doesn't matter, but you'll see in the next case, you'll see.
All right? So there's our 2 equations. All right? We're good because we only have 1 variable in each. All right? So you guys write that down. Mr. Hager, do you want me to distribute that stuff first?
Yeah, you're gonna have to get R by itself
Okay.
in one of,
Yeah. So guys, we're gonna distribute this stuff we're gonna do each equation separately, distribute, then we're gonna move some stuff around and get it by itself. I think we'll use the top equation. All right? So I'm gonna have 6 equals r minus 7 times 1.
In fact, since we only have 1 variable in the whole problem, look at the last one, because this one's going to be really different. I had a D and I had an R. 2 variables, I need 2 equations. I had a T and I had a D. 2 variables, 2 equations. How many different variables here? Just 1. It's only 1 variable, so really we only need 1 equation to solve it. We're not even really going to have to set up a system in this problem. You can get the answer that you need, really, just from the first equation. It basically says 6 equals r minus 7. Just move something to the other side.
Yeah. So we'll distribute first. 6 equals what? When I distribute, usually guys, we have the number in the front of the parentheses. In this case, it's behind it, but we can still distribute. Right, Gage?
Mhm.
Right?
Yeah.
Okay. Just making sure.
Yeah.
All right. So when I distribute this, Kevin, what am I going to get when I distribute this?
You want them all?
1r, yep. Minus 7, good. Now, I'm just going to move one thing, and I'm done. You want to do that? What do you want to do with the 7? Add 7, you're right. You got it right, man. Add 7. What else am I going to add 7, Zach? To the 6. Good man. Might as well finish it off now. 6 plus 7. What's 6 plus 6? Yeah, perfect. 13. Equals 1r. I know some of you guys do this. We can divide by 1. If you guys know r equals 13, that's fine. But I know some of you guys do this, right? So your rate equals 13 miles an hour, right?
Now, why don't we try solving for r in equation 2 and see if we get the same answer.
Can do that,
Right.
Mr. Hager.
So this one didn't work out to be a system. It actually worked out to be a lot easier. But if we did everything right, when we solve for r in equation 2, we better get 13. We don't need to do what we're doing right now, but I just want to check it because I'm curious to
Let's say you
see.
get the same thing.
We better, or something's wrong.
I need a calculator. That's not it.
So what now, Mr. Roy is taking 0.75 and he's going to distribute it out.
0.75 times 7. 5.25. And then we know that 0.75 R. I just distributed these two things, guys. Again, we just did it, like I said before, usually the number is before the parentheses. In this case, it's after it. It works the same way. If you want to rewrite it with the 0.75 in front, with the parentheses behind it, you can do that too.
What if you don't get the same thing? Because I just did it out and I didn't get the same thing.
Yeah, it looks like we might get
You
something.
get 1.
You end up with R equals 1, huh?
Yeah.
I'll have to check and see what
That was the one we used last year too.
what happened. Okay, because both of our equations are set up fine. Okay. 6 equals R minus 7 times 1. And then with the wind, it's a plus 7 because that's going to speed you up. And yeah, it does look like it's going to come out different. So I'll have to double check and see why that's coming out different. Let me check that. Okay, so for now, don't worry about why it came out different. I'll double check that and see why it comes out different. All right, so let's take a look. We either can do example 4 or 5. Okay, example 4 is about 2 people starting from the same spot in the same direction, and we want to know when they're going to be 10 miles apart because they're going different speeds. So it's like one person's going faster, so they're just getting further and further away from the other person. You guys want to try one like that? Because I don't think we did one quite like that. All right, what are the 2 things in this problem? Yeah, I think the labels this time are pretty clear. Okay, put Gene and Bob. All right. Do I know Gene's speed? Does it say anywhere in the problem how fast Gene is going? How about Zach?
Gene?
Yeah.
No.
It doesn't say how fast she's going? Sure, read it again.
Oh, 12.
12, yeah. Gene rode at 12 miles an hour. Okay. Do we know Bob's speed? 10. Okay. Bob rode at 10 miles an hour. Okay. It says, after how many hours will they be 10 miles apart? So, are they each starting at the same time? Are they each starting at the same time? What do you think, Caitlin? Yeah, it says Gene and Bob started bicycling from the same spot and going in the same direction. Okay, so they started bicycling at the same time, and they're going to stop at the same time. Okay, so that means their times are going to be the same. Okay, now we need their distances. Okay, who's going to travel farther? Who? Why is Gene going to travel farther? Yeah, because they're going faster. Okay, so they're going to end up traveling farther than the other person. All right, so let's call Bob's distance D. Okay, let's say Bob travels D units. Victor, how far is Gene going to travel?
Maybe 12 miles. I don't know.
So we haven't used this fact yet.
Probably 10.
when will they be 10 miles apart? So if Bob travels D, how would you represent 10 miles apart? Specifically, Gene's going to be 10 miles further ahead. Yeah? D plus 10. Right? So if you were doing this with your friend, maybe you went 50 miles and your friend went 60. Okay? The point is, however far you travel, your friend is going to travel 10 miles farther than you did. So if you went 25, they went 35. Okay. Now this one is going to work out just like one of the first two. Two letters. We have a D and we have a T. So we're going to need two equations and we'll use substitution. Okay. So I guarantee you this problem is going to work out okay. All right. Let's start with equation 1 and equation 2. Okay. Anybody tell me equation 1? Yep. D plus,
Just D. 10.
yep, equals,
12. Parentheses.
yep,
12. T.
yep. So you could put parentheses, or because it's just a number and a letter, you can put it just like that. That's perfect. D plus 10 equals 12t. Okay. Who can tell me my second equation?
D.
Yep,
Equals 10.
T.
t. Good.
Listen to you, boy. You're like so
Okay.
smart.
What letter do we already have by itself?
D.
D, and in which equation is it by itself?
Bob.
The second one. So we're going to take what D equals, and where am I going to fill that in?
Plug it into the first equation.
For what letter? Yeah, for D. Okay, so see, this is working out just like one of the first ones. So fill in 10t for D. So 10t plus, what's still on the left-hand side? 10 equals 12t. Okay, next step, how do I move the 10t to the other side? Good. Minus it. Minus it. Yep, 12t, take away 10t is 2t. And what about my last step?
Go back. Right.
Divide by 2.
You get
So what's the time?
5.
5 hours. Yep, it's not miles per hour because it's a time. So just 5 hours. So the question is, how long is it going to take for the two people to be 10 miles apart? It's going to take 5 hours.
On the test, is it
Boy,
gonna be
this is
bonus?
practice.
I don't know. Maybe we'll do one of the word problems as a bonus. We'll see. We'll see. Okay. Does that make sense? 5. Because think about, if one person's going 2 miles an hour faster than the other, every hour they're getting 2 more miles apart. Okay? So after 1 hour, someone's gone 12, somebody's gone 10. After 2 hours, this person's gone 24 miles, this person's gone 20. After 3 hours, this person's gone 36, this person's gone 30. Right? So they just keep getting further and further apart as time goes on. Okay, so that one wasn't too bad. Worked out pretty quick. Any question on that? All right, let's see if we can set up the last one. I don't know if we'll have enough time to finish it, but maybe we can fill in our table. Okay, it says a car left Detroit traveling 45 miles an hour. A second car left an hour and a half later. Okay, so I think this is a problem where maybe we should call our things car 1, car 2. Okay? Or you could say, you know what, first car, second car, if you want to do that. Okay, so let's label it first car, second car. Okay, and when I say car here, this is the first. First car left Detroit. Who can tell me something I know about the first car? Just read the first sentence.
The car left Detroit traveling 45 miles per hour.
Yep, the car left Detroit traveling 45 miles per hour. So what's 45 miles per hour? That's my rate. Okay, that's good. At least I know something. A second car left from the same spot an hour and a half later. Okay, let's just keep reading it. The second car traveled on the same road, and it met the first car after driving 4.5 hours. Okay, so now I know something else. How long was the second car driving for? It says the second car traveled on the same road and met the first car 4.5 hours later. So how long was the second car driving for? Count? Yeah. It says the second car met the first car after 4.5 hours. Okay? So that's my time of the second car. Now, here's something I think we can figure out. The first car left an hour and a half before the second car. So how long was the first car on the road before the second car? How long? Not a half hour.
2 hours.
A second car left from the same place an hour and a half later. So the first car had been on the road how long before the second one left? An hour and a half. Okay. Now, the second car drove 4.5 hours. The first car was on the road an hour and a half before that. So how long had the first car been driving? 6 hours. That's the tricky one in this one. Okay? So if your friend was on the road for 4.5 hours, and you left an hour and a half before them and then caught up to them, you must have been on the road for 6 hours. All right? Find the speed of the second car. So something tells me we're not going to know that. Okay? But look at the key word here. It says these cars met. So you each started from the same point. You each met at the same point. What does that mean about the distances you each traveled? They're the same. Okay? You each started at a certain point. You each met at the same point. So you must have each traveled the same distance. Here's my equation. And now I'm going to solve it.
And guys, because that's when we're giving you the amount of, we're giving you the time for both things. You just have to figure it out.
Distance equals 45 times 6. And distance equals 4.5r. Which one of those equations only has one letter? Equation 1 or equation 2? Equation 1. Let's figure out what equation 1 is. Distance equals 45 times 6. 270. Look what I just figured out. I know that the cars drove 270 miles. Okay. Is the question, how far did the cars drive to meet up? Corey? Is the question, how far did the cars drive to meet up? No, what is the question asking? Find the speed of the second car. Okay? We want to know the speed. Well, first we had to figure out, okay, the car drove 270 miles. Fill 270 in for D, because the distance is 270. So in equation 2, we get 270 equals 4.5r. And how do I get 4.5 on the other side? Good, divide. Okay, so the second car was going 60 miles an hour. Okay, so again, Mr. Ray and I know these are hard word problems. They're not easy. Okay, and it takes a ton of practice to just get good at them. But we'll practice some more tomorrow. So don't feel too discouraged if you're having trouble, because it's a hard section.
You guys, you gotta like give yourself the opportunity to understand it, so when you don't write the notes down, that doesn't help.
Okay, so homework tonight, worksheet. Okay, tomorrow we'll do a little review. And because these problems are so hard, we're going to give you the first half of the test as a take-home on Thursday.